Today we're very pleased to welcome Dr. Sjoerd van Ophem, and he's going to talk to us about time domain vibro-acoustic reduced order models and their potential for digital twins. So, welcome.
Thank you. Thank you. So hello everyone, welcome to my seminar. I'm glad that you all could make it, even with this nice weather outside. I can imagine you would also like to maybe sit outside in the sun for your lunch break. Before I start talking about this topic, I would like to first briefly introduce myself. Yeah. So about me, I'm originally from the Netherlands, from a small village basically here. Then I did my bachelor and master's in mechanical engineering at the University of Twente, which is here. After that, I went to Belgium to do a PhD in acoustics and vibrations in Leuven, which is here, next to Brussels. And it was in the LMSD group, so that's like the mechatronic system design group in Leuven. And I also stayed there for a while as a postdoctoral researcher. And then about half a year ago, I moved to Southampton to become a lecturer at the Institute of Sound and Vibration Research, specifically in the dynamics group. So that's where I'm based right now. And in this presentation, I will basically talk about the following topics. I will start with a small research motivation. Then I will explain a bit, as you've seen in the title, that I'm going to talk about digital twins. This is a bit of a buzzword, obviously, as you all know. So I would like to explain a bit more in detail what I mean by digital twins in the context of my research. And I will also talk about how we can use these digital twins to help become more sustainable, not only in the UK, but also Europe and hopefully even worldwide at some point. Then I will talk about stability preserving reduced order modeling. This is a method that we're using to basically be able to use digital twins for vibroacoustics. And then I will conclude my presentation with a few examples that will demonstrate hopefully how we can use these methods effectively for acoustic problems. All right, so I'll start with the research motivation. And as you probably, I think most of you are aware of this article written by the World Health Organization, which basically describes the burden of disease from environmental noise. So, for example, for traffic noise. And they show quite a, let's say, maybe impressive is the wrong word for it, but it's quite some alarming statistics where they say that at least 1 million health years of life years are lost every year due to traffic-related noise, only in the western part of Europe. So that's quite alarming, and it places the burden of this disease second after noise, air pollution. So it's quite a significant problem that we have to deal with. Also, in this figure on the left, you can see the impact of noise on Europe. So this is the European Economic Area. I guess this figure was made before Brexit, because the UK is still in here. But you can see that all the red points on the map are basically places where it's almost impossible to find quiet zones where you can actually be relieved of the burden of noise. So basically around every big city in Europe, you see big red spots, including Manchester. So it's not going to be, it's something that should be treated in the future to get like a bit more, let's say, pleasant society. So I talked a bit about noise pollution. Now, how is this related to sustainability? Noise is quite an important part if you want to go towards a more sustainable society. Because to get a bit sustainable, let's say, vehicle or sustainable machine or whatever you're working on to make it sustainable, here are some examples. You basically want to balance 3 parts. On the one hand, you have health aspects. So it could be safety, for example, of the vehicle. but also stuff like noise and vibration, which for us acoustic engineers is very important. So if you want to drive, for example, in a train, you want it to be hopefully not so noisy, so that people that are living around the train rails don't suffer a lot from it, and also the people that are inside the trains, obviously. Then we have environmental impacts, so like how much energy does the machine vehicle use while it's running, but also material usage and emissions. And then the third aspect is also important for a lot of companies is, of course, profitability. So we want to make sure that the product we're making is reliable, durable, and that it doesn't cost too much to produce. And so this balancing act is quite difficult. And as you can see, noise is mentioned as one of the aspects to consider here. So that's where the digital twins come into play. I will briefly explain to you what I mean by a digital twin. What I mean is basically that a digital twin is a virtual copy of an existing physical asset. So physical asset would be a machine or a vehicle, or maybe even like a full production line, or it could also be related to how we perceive sound. So if you have a virtual copy of, let's say, a human ear, that would also be a possibility. And very importantly, this digital twin behaves as if it were the actual physical twin. So that means if it actually behaves as a physical twin, it means that we can use this digital twin to make important design or control or maintenance decisions using some, let's say, some sparse sensor data from the physical aspect. So since this is just a definition, I'll try to make it a bit more clear with this slide here. So if you look a bit around in literature on digital twins, you often see the digital twins right with these digital twin layers that I show you here. So first layer that we have is obviously the physical system. So physical system can be car, compressor, but physical system also includes aspects as the physical sensors, so microphones, accelerometers, etc., shaker straps, and also data acquisition systems are part of this physical system. So, for example, speed codes or small boards like Arduinos. And like I said, even like you can include things in the physical system that are related to how we as humans perceive sound and vibration. So, for example, a model of an ear. Then we have the communication layer. So we have the physical system, we have some sensors on it, they measure something. And now we're going to send this data to the virtual domain. So everything in this box is virtual. And if you have, for example, a digital twin of a factory hall, then these sensors are placed around. So they are maybe not connected directly to each other, but they're only connected through, for example, a local network. So it could be some kind of Internet of Things, IoT type of connection, or perhaps connected via 5G or Wi-Fi. And this means that in the communication layer, we have to try to fix, for example, syncing these sensors, because you might have a few microphones that are all locally placed around, but they are not really talking to each other. And they might run at different sampling rates. They might be desynchronized. So in this layer, you try to put everything together. So this is what they sometimes call multimodal sensors, to basically try to get a coherent sensor information. Then we have the virtual system itself. So this virtual system is what I would see as a model of the physical system, as you can see here. So that can be, for example, a finite element model. I will show you some examples later of that. Or it can be some kind of lumped parameter model if you if you want. And also what I'm putting here is like a reduced order model. I will talk to you about reduced order models later. But the idea is that finite element models, as most of you probably know, are very large, and they cannot run in real time on a machine like this, like cheat codes. They're just it's impossible. So instead, we want to reduce the size of these finite element models so that they're still accurate, but they're much smaller so that we can run them in real time if we need to. And I also put here like some other types of ways that we could model a system, like nowadays lots of research going on AI, physics-informed neural networks, and that sort of thing. So that's what I would also put in this virtual system block here. And then most importantly, we have the application layer. So this is what we would say is like the added value of a digital twin. So what does it bring to the table that we don't already have in the system without this digital twin? And it could be a lot of potential applications. One that I will show you later is what we call virtual sensing, which is a monitoring approach where we basically, with a few sensors and this virtual system, we can extrapolate the sensor data to the full field. So we can do like full sound field predictions or vibration field predictions. But we can also use a digital twin to help us with condition monitoring, so to see when a machine is starting to break down based upon the sensor data that we get. We could also use it in a design context to, for example, to run what-if scenarios, meaning we can change parameters to see what's the impact of changing these parameters on the system. Oralization is another application, so listening to the virtual object, active control, etc. So there are lots of different scenarios that we can think about. So in my presentation, I will mainly talk about reduced order modeling and virtual sensing. I'm not doing research on all these aspects of this slide here, but I just wanted to mention a bit of like what type of framework I'm thinking about when I work on this topic. So now, how is this related to sustainability? So for traditional methods, and for traditional methods, I mean like either the school where you just mainly use models, so you are mainly working on simulations, or on the other hand, where you mainly do measurements. So that's what I would call traditional methods. I don't really fit names, maybe not the best. But the idea here is that you usually focus on one of these three aspects. So either you try to reduce the noise of an object, so you're mainly working on the health aspects, and maybe not so much on the environmental aspects and profitability aspects. But we want to go towards a system-based approach where we do all these things concurrently. And maybe we will not find the best solution only from a health perspective. So maybe we will not find a solution with the most noise reduction, but we will find hopefully a solution that gives us an acceptable amount of noise reduction, but also keeping in mind that we want to improve the environment and make sure that profitability is also fine. So that's a bit the way I see how we could use these digital twins to strive for more sustainable products. So that's the research motivation in a nutshell. I will now start talking a bit more about the technical aspects that I've been working on. I would like to start with stability preserving reduced order modeling. So we start basically from a modeling approach. We have, like, let's say, a car cavity. This car cavity has certain acoustics that we have to take into account. And we know that if we just look at the continuous like the partial differential equations, we basically are looking at the wave equation here. And then the common approach is to use finite element methods or boundary element methods to discretize the domain with small elements. and then solve it like basically like that with the discretized spatial domain approach. And thus we end up with like a bunch of ordinary differential equations that we can try to solve with a computer, because these are just linear algebra equations in the end. So yeah, like I said, we can use finite elements or boundary elements methods. I just make a small comparison between the two, just to argue why I'm mostly looking to finite element methods. However, I think both methods have their advantages, obviously. But for the reduced order modeling approaches that we use, the advantages of the finite element methods are that you can get sparse matrices that are frequency independent, although they're not always frequency independent. We'll come back to this a bit later. And that they are easily calculated in time domain. So that's the reason why we want to go for a time domain, is because for a lot of these digital twin approaches, you do kind of like an online type of approach where you measure and you directly want to know the influence of certain sensor signals on the system, instead of in frequency domain approach where you basically have a certain delay that you have to take into account when you do signal processing. Of course, with the PEM, you have certain nice things there that are not in the finite element method, like, for example, that the radiation conditions, the Sommerfeld radiation conditions, so the conditions where you have an exterior problem in which the sound is basically radiating to infinity, which is, you can basically see it as like standing in the desert and screaming. The sound will just continue to propagate until it's basically dissipated in the air. This is what we try to model with the Sommerfeld radiation condition here. So for the finite element method, we need to use some numerical tools to kind of simulate that. And I'll show you in a bit how we're going to do that. But the most important part about this slide is just that I want to say that the jury is still out on what method could be best for which application. I'm not like necessarily only a finite element guy, but I would like to use them in this particular case because I think they make more sense for this application. So model order reduction. I talked already about it a bit, but what is it actually? So the goal is to reduce the size of this equation here. So where we have like three matrices, M, C, and K, the mass, stiffness, and damping matrices. They're quite large usually. Like for industrial applications, it can easily be more than 1 million degrees of freedom. And so you basically have three matrices which are absolutely huge. And what you do with reduced order modeling is you try to find two matrices, W and V. And what these matrices do is they'll pre-multiply this big matrix here with W, and you post-multiply it with V. And then the idea is that you end up with a very small matrix MR that hopefully still has the accuracy of the full matrices. And so there are lots of different model order reduction techniques available, but they're all based around this idea, at least all the projection-based model order reduction techniques, that we have to find a suitable W and V to get this small matrix so that we can run this equation perhaps hopefully in real time in the actual application. So there are two cases here that I wanted to quickly mention. So W and V, you can actually choose W equal to V. So that's what we call a one-sided projection. And this is actually in a lot of applications, it's quite a good thing to do, because we will see in a minute that if you do that, you can prove certain conditions that are true for the matrix M, to the big matrix, that they are also true for the small matrix after doing this projection. So, for example, positive definiteness properties of this bit matrix would be retained in a small matrix if you use this one-sided projection. But if you do the two-sided projection, then perhaps this is not the case. So that's one reason why you would choose that. So why does model order reduction work? This is just a bit of a thought experiment, really. So let's assume that we have like a beam that's clamped on one side, and we try to model it with finite elements. The finite element solution will include, for example, this solution here, which if you would have a clamped beam with a force on the end, this is a solution that makes perfect sense. However, if you look at finite element solutions, you would also get at high frequency solutions like this that perhaps don't make a lot of sense because the finite element methods, because it's discretized in space, you can only get accurate solutions to a certain frequency. Above that frequency, the solution is not valid because the discretization is not fine enough. So this solution here would be non-physical, but however, it's still included in your full order model solution. So if we would build a solution space that includes this solution here and not this solution, then perhaps we can get rid of a lot of non-relevant information. That's and that's why model order reduction is a technique that basically tries to do this in a mathematical way. And yeah, so that's a bit the idea. Now, what type of method am I using? The one that I'm using is called the Krylov subspace model order reduction. I think a lot of you are probably familiar with modal reduction. So you use like modes to build like you basically say that the solution of your system is like the sum of mode shapes. This method is a bit different because it works on the transfer function instead. So what we want to do is, given a certain input and a certain output, we want to approximate the transfer function or the frequency response function using power series expansion. So power series expansion, what it does is, let's say we have this blue line here. This is like the solution that the full order model gives us. It chooses a certain frequency. Let's say the frequency is here in the middle. And then it starts doing this power series expansion. And the more moments you take, so these moments are the derivatives of the transfer function around that frequency point. The more moments we take, the better we can fit this frequency response function. And you see here this red curve fits the frequency response function very well from 0 to, let's say, 300 something hertz. And after that, as you can see, it stops behaving well. So that's where it might be beneficial to add more moments into your expansion to get like a wider fit, basically. So this is the idea of Krylov subspace reduced order modeling, is that we find a way to do this power series expansion mathematically. But it doesn't do it like explicitly. So it doesn't directly calculate these derivatives here that we need. Some people tried to do this in the past, but they found that this becomes unstable after only taking a few of these derivatives. The algorithm starts to become unstable. So it's not a very good way to try to do this fitting here. So instead, some mathematicians found a way to do this implicitly. So it's like a mathematical procedure that doesn't directly calculate these derivatives, but of which you can prove that after running it, you manage to get these derivatives fitted anyway. So if you're interested in that, I would suggest reading this PhD thesis. It's quite an involved procedure, so I'm not going to explain it today, but it's quite interesting to read if you're into this maths. All right, so let me quickly check the time. Okay, we're going to speed up a bit. So these are currently one-order reduction methods that we did research on, where we successfully found a way to do one-order reduction in the time domain. So you can see, I will give you a few examples. We started basically on the left with interior problems with proportional damping. This would be like the easiest case, both for purely acoustic problems and vibro-acoustic. So where we also have like some kind of structure inside of the model. And the thing is, if you do this procedure, the stability under reduction is not guaranteed. So you have to somehow find a way to get the stability preserved under reduction. Why is this the case? So if you look at like any finite element method, there are certain stability conditions that these matrices can have or should have to become stable. And these are some of these stability conditions. Now, these are not necessarily required stability conditions, but they're sufficient. So it means that if you somehow have a system that conforms to these stability conditions, you know it's stable. But it doesn't mean that systems that don't have these conditions are necessarily unstable. But the stability preservation under reduction, we found out that if we don't adhere to the stability conditions under reduction, that we usually end up with a system that is unstable in the reduced order form. So how are we going to do this? So we're using one-sided projection. As I mentioned, this preserves the definiteness properties of the matrices. So that's the reason why we use that. And I'll give you an example on how we did this stability preservation for interior vibro-acoustic systems. So a common formulation to solve it in the time domain is this UP formulation, as we call it. So U is basically the displacement of the structure, and P is the pressure, the acoustic pressure. You see here we have these subscripts S and A are basically structure and acoustics, and the coupling is done via these KC matrices. So that's the coupling, the two-way coupling between the structure and the acoustical part. And as you can see, these two matrices, they don't adhere to this stability condition in the slide here because they're not symmetric. However, this system is stable if you run it in time domain. But in the reduction process that we did, we found out that if we do this without any adjustments, that we do get instabilities. So if we run the reduced order model in the time domain, we do get instabilities. And the reason for that is based on these coupling matrices. So let's say we have a certain vector. So this vector can be seen as a one column in this matrix V here. So if we calculate then if we do this multiplication with this vector, we find out we have basically two constants here, which are fine, but they will preserve their stability or definite properties under this reduction. However, this third term, you see we have like x1 and x2. So x1 is the structural part of the equation, x2 is the acoustic. This term here can be positive or negative. We don't know. And that's why we cannot prove that this reduction leads to stability. So what did we do to solve it? We used a modified formulation. This modified formulation, as you can see, actually has symmetric matrices for M and K. And that's the reason that this formulation does work while the other didn't. And if we would look at the definiteness properties of the coupling matrix, because all the coupling terms with this modified formulation, which, as you can see, it works on the velocity potential instead of the pressure itself. So we solve for the acoustic velocity potential phi and not for the acoustic pressure. All the coupling matrices are now in the damping matrix instead of in the mass and stiffness matrix. And in this case, if we do the same calculation, we end up with a term of which we can prove it's always bigger than or equal to 0, which means it's the definiteness properties of this damping matrix are known. So that's the main difference of this formulation as compared to the previous formulation. So then we did some extensions. We went to tackle the Sommerfeld radiation condition as the next step. For that, we used first infinite elements. And for this infinite element formulation, actually this approach that we used in the previous slides actually works without major adjustments. So, which is quite nice. So this infinite element formulation has frequency independent matrices. And recently we extended this formulation. This is work I did together with some people at Siemens to be able to build like a very compact, convex, let's say truncation layer around an object, like for example, for this 1010 submarine. And we can solve it with infinite elements that are closely placed around this submarine here. Which is very nice because during my PhD, I had to work with spheroidal domains. Sorry for that. Which basically means that if you want to look at objects which have a very big aspect ratio, like the submarine here, you end up with a huge computational domain because of the spheroidal aspect. And we found a way to extend this formulation to basically calculate objects like this, which leads to a significant reduction in the degrees of freedom. So some examples. So for this 1010 submarine here, for example, you can see we did the simulation with the monopole source placed here at the tip of the submarine. And we went from, let's say, almost 500,000 degrees of freedom to a reduced order model of 90 degrees of freedom with a relative error of maximum 1% from k times a, so the wave number times a for 5 to 50. So it's quite a big frequency range where we can use this model. And some other examples. So here we have like a card cavity with basically we modeled also the roof here. So it's like a vibro-acoustic model where we excited the roof with the force and then try to calculate the response because of the sine sweep excitation, and a loudspeaker example here where we just excited the woofer of the loudspeaker with a 0.4. And so for these two models on the left, we also got a reduction that's maybe the size of the reduced order model is maybe 0.1% times the original size of the model, while maintaining, like in this case, I think 0.1% error, relative error. So it's quite good. As you can see here, like basically the transient response is basically indistinguishable from the full order model response here. Yeah, so that works quite well. Then we did some further extensions to porous materials. So the challenge with porous materials is that they're modeled with frequency-dependent matrices. So, like for example, think about admittance or impedance boundary conditions. They're typically not constant as function of frequency. So this brings a bit of extra challenge to the table. And here I have an example of again a card cavity where we use admittance boundary conditions to model the leather seats, the carpets, and the roof. We did actually model with some structure, and we used like basically a Mickey model and a GCA model for the frequency-dependent impedance. And we can actually do this in the time domain now. So what we do is we approximate the frequency-dependent curve with a rational function, and we transform that to a time domain formulation, which means actually that the degrees of freedom of the system, they are increasing because of this. But then when we do the reduction, you see we go from a model that's around 400,000 degrees of freedom back to a model which is only 300 something degrees of freedom. And that actually works quite well. We also looked at perfectly matched layers. That's like an alternative to infinite elements. Again, a submarine, I'm not doing research on military aspects at all, but submarine is just a nice shape to do these very high aspect ratio simulation on. And so here we did PML simulation. PMLs are quite tricky to do in the time domain because they have like frequency dependent properties again. But we found a way to go from a time domain model around 700,000 degrees of freedom to a reduced order model of 72. So that's quite a big change in size. Okay, so the last part of the presentation, I will talk about the usage of these reduced order models in actual applications. And I would like to start talking about this application here where we have like oil sump type of structure. So this is like something you could find on the bottom of a car, for example. And yeah, so we have like for this particular application, we have a virtual model. So that's I will show you in a bit how it looks like. And we did some measurements in the lab in a semi-anechoic room to get some data. So we basically have the data on these specific microphone locations, and we also place some accelerometers, as you can see here on the structure. But what we want to do actually is to get to full field estimation of the sound and also of the sound intensity. So what we're going to do is we're going to use a state estimator. So this is an algorithm which can basically couple the physical physics-based model, which we will use a reduced order model for, and the sensor data in a smart way. And the state estimator, what it does is, well, the algorithm that we're using is called a Kalman filter. And what it does, it's on the one hand, it's running the model. So the model, in this case, for this example, let's say we have a car that's driving. The model predicts where the car will be based on this current location. And it's purely based on some mathematics. It could be, for example, you could assume that the model says, okay, it's driving with a constant speed. And then based upon that, it will predict the next step with an Gaussian uncertainty of the location. Then we have a measurement, which could be like a GPS type of thing, a GPS signal, which also has some uncertainty on it. And the whole idea of this algorithm, this state estimator, is that it combines both of these predictions together, and you get an estimate which can be a lot more accurate than these individual measurements or individual models by combining them in a smart way together. So that's what we're using. So, like I said, the structure we're using, it's made of steel, and it's quite a tricky structure actually because it was manufactured by deep drawing, and so there is quite a significant variation between. We had like 5 of these in the lab when I was at Leuven, and they all had different resonance frequencies. So it's quite tricky to model these. But we tried doing it with the finite element methods, where we used shells for the structure, infinite elements for the Sommerfeld condition, and we used some patch-based updating to match the frequency response functions, more or less. So what it means is that we divided the structure into a few patches, and per patch we changed the Young's modulus, so that's the material properties. So we did model order reduction on this. So it was 54,000 DOFs, and we went to 50 DOFs with a very low error. And then we converted this model to state space. So state space is just a way to rewrite the equations to a first order ODEs in this type of shape here. And so we can use this directly in this Kalman filter. We placed a few sensors around the structure, and basically we started doing the measurements. Here we have an idea of how this looked. And we used only 4 microphones we used 5 microphones, 6 microphones in the Kalman filter, and 4 microphones. We just placed them to check if the actual results that we were expecting were obtained or not. And here you have the comparison. So the admittedly a bit difficult to see dash line is a simulation only result. So we used the force signal that we measured just to run a simulation. The black curves are the microphone outputs that we got, and the gray curves are the virtual measurements that we got through this Kalman filter approach. And so you can see that the response, albeit not perfectly matching, it matches much better than the simulation only results that we got. And so we are actually, with this approach, then able to do full field predictions that are in line with these results here. So we extended it as well to sound intensity predictions. So I used the PP probe to measure the sound intensity in a certain direction on these locations around this oil sump. So the locations plus the directions are shown. And I compared these measurements that we did. So I looked at the intensity level in this case, and I compared them to the intensity levels that I got from using this Kalman filter approach. So again, not perfect results, but I would say it's still quite a good match of the intensity level. So as you probably know, the intensity, the sound intensity, you could use it actually to calculate the sound power by integrating this over this full sphere here to calculate the sound power of the object here. So you could perhaps use it for that as well. And we can then make like these nice little animations of the instantaneous sound intensity as function of time. So this is time domain simulation. Time domain prediction, because this is what's coming out of the Kalman filter predictions here. Okay, so second example, I still have a few minutes hopefully to show this. This is an example I worked on together with Siemens. And it's about the direct field acoustic testing. I know John is very much into this topic. But it's basically the idea is that we want to simulate the acoustic loading of a payload or spacecraft during launch using controlled acoustic conditions. And since we cannot just launch a satellite into space to test it, it's too expensive, we usually have to do ground-based environmental testing. So there are 2 ways to do it, more or less. So we have like large test facilities like reverberant chambers that are basically huge to do this. But of course, you need this chamber and facility. So you need to move your satellite to this location. So it can be quite costly, time-consuming method. So instead, what some people are doing is use direct field acoustic testing, which can be done in like a standard factory hall, basically. And they just put a whole bunch of loudspeakers in a cylindrical array around this satellite component. And then they make sure these speakers are exciting the structure in a way that basically is controlled. And yeah, so this is a good alternative to reverberant rooms if you don't have these facilities. Yeah, so what we wanted to look at is basically, as you can see, there are some microphone locations around this object that we are using for the measurement to check if the acoustic field is like we expected. But we wanted to see if we can also use this, basically this digital twin approach to get an idea of the sound pressure level on locations where we are not measuring. So, so that was the motivation of this research work. And we did this like with basically a very tiny mock-up setup. So you can see here we have like we built like a small speaker array, so like maybe this small. I think it's probably very similar to what you have, John, where we basically put a whole bunch of microphones in. So we used 46 microphones, 45 speakers, and as you can see, it's not the anechoic room at all. We just used the basement of Siemens basically because that was available to us. Then we built a numerical model. So we used here like a combination of lump parameter modeling for the speaker dynamics. So that's like an electromechanical model combined with the finite elements model, where we use this flexible infinite element formulation to get this mesh basically. Yeah, and so then we did the measurements. We put a grid above this speaker array, and we hung the microphones like down. So as you can see, it looks a bit messy, but these are the 46 microphones, like you can see here. Took like perhaps like one full day to get all the cables connected and all the microphones calibrated, but you know, that's quite a big measurement. So then we did the virtual sensing experiment. So how we did it is just we ran like a MIMO random control algorithm to basically get this algorithm to work like in a traditional way. So Siemens, they have like a tool called pretest analysis, where you can basically, based upon a whole bunch of microphones, select the best ones to use. So we measured it. We did some filtering on the time domain signals. We didn't use any test specimens to make the setup a bit easier. And then we chose some microphones to be put in this gamma filter. So we did 2 experiments, one with 6 microphones, one with 12. And the other microphones were used as references. And the reduced on model that we used is, well, it's a bit larger now. It's like around 570 states. That's what we needed to get something that was accurate enough for this specific application and frequency range, which is indicated here. So these are some results. So as you can see, we, well, in this case, you should ignore this FRF-based approach, because that was a different method that we also used. That was more like what Siemens wanted to do than what I wanted to do for my research. But the reference and the simulation are compared on the left. So this is just purely based on simulating the system without any gamma filtering. And then on the right, we have the comparison after running this digital twin approach. And we also compared the frequency domain. And yeah, so what we wanted to achieve was basically this reference here. So how it works is you set like sort of a plus minus 3 dB or plus minus even less dB basically pattern that you want to have. So the frequency distribution has to be within this range here. And you can see on the left that it's not really the case, while the figure on the right does give it. And so it should be within these bands, because the control algorithm was set to do this. So the predictions here on the left, just running the simulation, were not very accurate. Well, they were much more accurate for the gamma filter predictions here.
Right, about time.
Yeah, right. Well, I was already finished anyway. But so just to conclude, I hopefully show you that the digital twins can help us to get more sustainable vibro-acoustic systems. And I showed you an approach using finite element methods and reduced order modeling to make it work for the applications that I've just shown you. And yeah, I will continue doing this work also in the future at the ISVR. So if at any point you think like, this would be an interesting topic to work together with me on, within the CDT, for example, or in other types of collaborations, then I would always be glad to have a chat. So thank you a lot for your attention.
Reduce a model. Obviously, if you're going to run it real time, you're only going to do this once. It doesn't matter. But if you're going to like be updating a model, maybe it's moving and you've got things changing, you have to reduce it over and over again.
Yeah.
What's that kind of cost like?
Yeah. So the cost. Let's first talk about the simple case. It's you have to run a few full order model simulations to get it. So it. Like I said, it's this Correlate-based subspace is around a certain frequency that you're doing this expansion. So you have to basically solve it at that specific frequency. So you do one full system solve, and then you do this moment matching, which is not dependent on the full order system size. So that's pretty quick after you've done that. If you want to look at different situations, different parameters, there is this thing called parametric model order reduction. So that obviously takes much more time to do this upfront. But if you know upfront, like my parameter space is between -2 and +2, whatever it is, you can use this upfront to calculate this parametric model. But that's the funny thing, that a lot of literature, they say, this offline cost, it can be anything because we can just run it on a supercomputer. But obviously, that's not really an approach I like that much. I would also like it to be within a reasonable calculation time for, let's say, your own workstation or laptop.
Then in general, to reduce a model, it's more expensive to reduce than to run it in its entirety. But once it is reduced, then it's very quick.
No, it's so. If the traditional way to run it is if you like a frequency sweep. You calculate the frequency response function at, let's say, every hertz. So at every hertz, you have to do a full system solve. And this Krylov approach is just calculating it maybe at 3 frequencies. And then it's using this power series expansion to do the interpolation between these frequency points. So it is much faster than running the full order model in many applications. And that's when if you go to nonlinear systems, then it becomes a different story. But these systems that I've showed you here are mostly linear, so it's much easier to do. So there is still ongoing work as well on this stuff.
Okay. Any other questions?
So is it like quantizing the frequency spectrum? Interesting.
So
are you like, is it like that? I don't know if I can explain that. Are you like quantizing the samples that you take in at specific intervals and then expand the results from other frequencies?
You mean like how I choose these points? Or?
Yeah.
Yeah, so we actually developed, when I was at K11, we developed an algorithm that does this automatically. So you choose your frequency range. It just takes a point in the middle of the start. It does this moments matching. And then at some point, the algorithm, if you do like 50 moments, it usually stops working very well. So then it cuts off the moment matching and it starts introducing a new point, which is basically the frequency range you didn't cover yet. And again, it starts doing this. So it's like a sort of an adaptive method for automatically choosing these points for you. It's not necessarily the best way to do it. It doesn't give you the smallest reduced order models, but it's like economically from a calculation perspective to do it like that.
But eventually ends up calculating for every frequency adjoining the starting one.
Yeah, so the reduced order, the projection basis that we're calculating, right? So if it somehow has overlapping information, it will automatically throw it out because we do like an ortho normalization process on this matrix. So any linearly dependent factors that we get, they are removed through this orthonormalization process. So you might have this thing that at a certain frequency you have overlapping information if you do this process, but it's not really a problem because the mathematical procedure that we use throws them out at the end. So. We can have like this.
We might need John to do more of this question session then. Well, thank you very much again.
Thank you for your attention.